Hello, everybody. Thank you for connecting today to the webinar. Today, we are with Bob White. I think he doesn't need introduction because I think he's a very well-known figure in the industry. For those of you that doesn't know, it's a recognized expert in power electronics and magnetic design, and he has decades of experience developing different topologies for high performance applications. Hi, Bob. How are you?
Hi, good. Thank you, Elizabeth. Thank you to Frenetic for hosting this webinar today.
I think everybody is waiting for your presentation, but I wanted to share something in the beginning with everybody who is connected now in this webinar. I would like to show you the new version of Frenetic AI. For those of you who have been connected in our latest webinars in these last months, you know, probably some of you have an account in our version 1, but let me share with you. I wanted to share with you the new version because I think, although this is not totally official now, we have not launched it yet. I would like to share something with you today because most of you are have been with us connected in every webinar. I wanted to week by week. So I only wanted to show how is the new look and feel and how accuracy is the new model of simulation with Frenetic AI. I'm going to use a very simple example to show you how it works. So let's use the flyback topology with 20 and design converter. We are trying to find a balance between processing speed and results. So at the beginning, this kind of tools and online platforms, it's especially with AI, it's very important the accuracy. So it takes more time than expected at first time, but our team is working in the speed of the process of all the calculations behind the Frenetic AI. So let's wait a couple of seconds. Okay. Okay, we have the electrical circuit diagram, and we have also now we have the action of download the LTSpice file. We have all the parameters, the magnetic aspects, and then we can suggest magnetic design. We need to wait another couple of seconds. This is good because now all the quick simulations you have in this tool in Frenetic AI is going to save here in the left part with now is new project 1, new project 2. Now we are running the new project 3. So now the version 3 has memory for all the projects. And for those of you who have the magnetic simulator license, you could move all these specs and all these calculations directly to the Frenetic magnetic simulator here in this button in the both path of the options near to the LTSpice access. Of course, if some of you don't have an account yet, I'm going to enable the registration option So you can access to try directly this version of Frenetic AI. Access is limited, so maybe that's why it takes more time than expected, but we can have an exception today for those of you. So now we have the second calculations, the magnetic specs, the design with the core losses, the winding losses, and the maximum temperature approx. This is also based on the calculations and model calculations we have in Frenetic Magnetic Simulator. You are going to see better examples with Bob in his explanation now, but I only wanted to show you a little bit of an advance of how it's going to be Frenetic AI, and this is the first look to the version 3. So I'm going to copy for all of you the link, so you can access with the same credentials, and I'm going to activate now the possibility of register for those of you that have not have an account yet. And yeah, I'm happy to hear feedback from you. So thank you, Bob, for this couple of minutes to explain this, and you can start with your presentations when you want.
Okay, so you should be seeing my screen now.
Yes.
Okay, so yeah, so today we're going to talk about the flyback converter that you were just showing, and the flyback converter is very popular. I mean, given that every mobile device charger in the world is a flyback, there's probably more flybacks converters in the world than anything else. It's the simplest of the isolated topologies, but the leakage inductance, even though it's a small parameter, plays a big role. So, so first of all, thank you to Frenetic for hosting and making this webinar possible. We're going to talk about focus on the leakage. I'm not going to talk about the operation of the flyback itself. I mean, that's a kind of an introductory topic. Hopefully you already kind of understand that. We're going to take a very detailed look at what happens when you transition from the on time, when the switch is on, to the reset or demagnetization time. And I'll start by doing that without the leakage inductance, just to kind of get oriented. And then with the leakage inductance, things get more complicated. And then understanding the loss and the calculation. There are some circuit design techniques I'll briefly discuss to minimize that loss. But really, the goal is to let's minimize the leakage in the first place. And that really comes down to the windings. And then I'm going to use the Frenetic platform to show how you can explore different, basically windings and different designs to get an improved design with lower leakage. Okay, so let's start with the flyback circuit and the model here. And the flyback inductor, really, it strictly is a flyback inductor. I'm going to use that term. Sometimes we call it a flyback transformer, but I'm going to use the term flyback inductor. And we're going to model that as a combination of an ideal transformer with a turns ratio N primary to N secondary, and the magnetizing inductance, Lmag. Now, it's important that this Lmag is not a separate inductor. It is the inductance of the flyback inductor, but we break it out for modeling purposes to help us understand the operation of the circuit. So it's not a separate inductor, even though that's what it kind of looks like here. Okay. So we start with the flyback converter, and it's on. The switch has been on. We've been applying positive volt seconds to the primary. We're building up flux in the core. We're building up a primary current. And ignoring the leakage, what happens right as the switch is turning off? Okay. So there's a current in the drain in the primary, and the magnetizing current, it's at some peak value. the secondary is reverse bias. There's no current in the winding. The capacitor is supplying the energy to the load. Okay? The voltage here is approximately 0. Okay? The voltage on the primary is equal to the input that's being applied to the magnetizing inductance. And we turn the MOSFET off. And what happens to the circuit model here? Well, in the most simplistic thing, this would just become an open circuit, the switch. But really, it becomes a capacitance. It's the output capacitance of the switch, the COSS. Now, there's other capacitances. There's winding capacitances. We're going to see there's a capacitance of a clamp diode and straight capacitances. I lump this all together. It's a COSS. Now, as a MOSFET, this capacitance is nonlinear. It's large when the voltage is low, and it gets smaller as the drain to source voltage increases. But we're just going to treat it kind of as a linear capacitor. So we've turned off the switch. We have this capacitance. We have the drain current, which is equal to the magnetizing current. Okay, the voltage here is still approximately 0, and this starts to ring. This inductance starts to resonate with this COSS. But the reality is that during this time interval of interest, this transition time, the current doesn't change very much. This really looks like a current source driving into a capacitor. And that's the way we're going to model this. Okay, so we model this really as a current source driving this current into this output capacitance. Okay, the voltage on the primary, voltage across here, is the input less the drain voltage. Okay, and what we see is this is going to start charging. Now I'm going to define something called the reset, V reset. This is going to be an important parameter. And it's basically just the reflected output plus diode voltage to the primary. So this output plus diode reflected by the turns ratio back to the primary, I'm calling V reset. It's going to be a key parameter I'm going to use over and over and over again. Okay? So what happens is here that the magnetizing current charges up the COSS. Okay? And it will rise, eventually reaches the input voltage. Okay? And when it does that, then there's basically no voltage across the primary, right? Because the voltage across here is equal to the input. So there's 0 voltage here, but it doesn't stop there. It keeps charging. And it's going to charge up to the point where the voltage here is equal to the input plus this reflected voltage from the output. Okay? And the voltage across here is now negative because of this voltage here is higher than the input. By the way, I've defined the polarity. This is negative. And what happens here? Well, that reflected voltage here is equal to the output, and we clamp. Okay? I mean, if we try and increase the voltage across here anymore, we actually end up forward biasing this diode. Okay? And the voltage becomes clamped, and the current will now divert from charging the drain through now this magnetizing current, and this ideal model flows through the primary of this ideal transformer, which then gets reflected out to the secondary, and we start delivering energy to the secondary. And so the drain voltage is clamped, and the voltage across the magnetizing inductance is clamped. And we are now delivering the energy that was stored in the magnetizing inductance, the flux that's in the core, is now being delivered to the secondary, and the voltage here is constant. Okay. So this is the turn off without leakage inductance. It's becomes fairly straightforward. We go from on to where we're charged, the on time, where we're storing energy in the core, in the flux, in the magnetizing inductance, to now this reset or demagnetization time, we're delivering that energy to the output. Now, when we bring the leakage inductance into the picture, it gets quite a bit more complicated. But now, what do we mean by leakage inductance? So here's a cross section of like, we're going to see this later. We've got a primary, we've got the core, the primary, the bobbin here, the secondary. We've got some insulating tape between the windings, and we've applied some positive volt-seconds to the primary. We've stored some energy. We now have flux in the core. We have energy stored in this inductance. Okay? And so these green lines here show up. This is the flux, and this flux is coupling both windings. Okay? But there is some flux because these windings are not exactly overlapping. There is some flux that only the primary winding sees and not the secondary. And that flux is a leakage flux. And the flux then becomes the leakage inductance. So the leakage inductance is result of, and we don't have this perfect coupling between the two windings. So when we apply this volt-seconds to the winding and we're building up the flux, most of the flux will be coupled by both windings, but not all of it. And this is the leakage inductance. Circuit-wise, we model that as a small inductance in series with our other model, with the magnetizing inductance and the ideal transformer. So all of this model here in the dashed line of the flyback inductor now has two magnetic elements and this ideal transformer. So in the circuit, as we are now turning off the MOSFET and it's becoming a capacitance, the voltage is still about zero. The voltage in the primary, again, is the difference between the input and the drain. And we've got this magnetizing current. Again, it's large. It's not going to change during this interval. And so we're going to be thinking of this as a constant current source. This is driving into the drain. And because we have this loop, Kirchhoff current law says that this current is the same all the way around, okay, for right now. Okay. So the current in the leakage inductance, the magnetizing, and the drain is all the same. Now, that voltage that's applied to the primary is split between the leakage inductance and the magnetizing inductance. These two inductances form an inductive voltage divider. And so we have this voltage dividing. We're starting to charge the capacitance, but this voltage is split. The primary voltage is split. We have this leakage over the sum. This is a voltage divider term. Okay? And so that voltage applied here. So what happens? Well, the drain voltage, we're charging that up as before. That current driving into that output capacitance is going to drive up the drain to source voltage. Well, that means that the voltage cross here, again, as we saw before, will go zero and go negative. As this drain voltage becomes greater than the input, the voltage across the magnetizing inductance will become negative. That means the voltage across the secondary goes from negative to positive. In the meantime, the voltage across the leakage, which was originally positive, goes from positive to negative. Now we have this voltage divider. Now, when the secondary voltage reaches the output plus the diode, and the diode becomes forward biased, okay, it clamps. Okay, the voltage across this winding can't increase anymore because basically this capacitor is so large it looks like a voltage source. The diode looks kind of like a voltage source, and so we stop, and the voltage here becomes clamped. we're going to change the model up a bit here. So we're just going to treat this reflected voltage from the secondary as a constant voltage source. Kind of makes things a little bit simpler. Okay? And it's equal to this minus, it's minus because of the way I've defined the polarities. And it's equal to the turns ratio times the diode times the output voltage. So this is the reflected output voltage being applied back across this magnetizing inductance. Okay? And now, because this is a constant voltage, we have that this leakage inductance is resonating with the output capacitance. The magnetizing inductance is kind of taken out of the picture because it's got a constant voltage across it. And what happens? Well, we still charge up that COSS. And what would be the peak drain voltage? Well, we can do the math. We can say, well, what's the energy transferred here? What's this half Li squared plus the initial half CV squared, and where do we end up with? And we can solve this. This is Circuits 101. Okay. And you say, well, what is this? Doesn't look so bad, right? But the problem is that this leakage inductance is measured in microhenries. The output capacitance is measured in picofarads. And so the ratio of that is like on the order of 10 to the sixth, more or less. And so now we end up with a pretty big term under even though it's under the square root. The square root of this is 1,000, 10 to the third, and we can end up with a very large peak voltage on the MOSFET. Well, we don't want to pay for a 3,000 volt MOSFET, but I'm going to give you a little preview here. This actually understates the energy delivered to this capacitance, and the voltage is even greater. So to prevent the voltage on the MOSFET from increasing sort of without limit, to 1,000 volts or more, okay, we add a clamp circuit. Okay, we are going to limit the voltage that this across this winding, and we do it with a diode and with some sort of clamp voltage. Okay? Now, this can be implemented in different ways, but this does mean here that the maximum voltage on the switch is the input plus the clamp. And that becomes an important design parameter for us. Okay? So we don't want MOSFETs rated for thousands of volts. We want MOSFETs rated for hundreds of volts because that's what's cheap and readily available. Okay? So at this point, once we clamp this voltage, once this voltage can no longer increase, there's no more C dV dt, okay? And this current will divert into the clamp. The diode starts conducting, and the current is diverted to the clamp. Let's take a look. We'll take a look at that in a little more detail. Now, how do we implement that? Well, one way is we can use a transient voltage suppressor, which is kind of a form of a power zener. It's not really a true zener diode. It's more of a specialized power zener. And we like this because the TVSs are rated for high surge peak power. But it limits our choices, and also they're kind of pricey. Okay, so it's simple, less PCB area, but the cost and the power dissipation in the semiconductor device are the disadvantages. Most commonly, the clamp is created with an RC circuit. So the RCD clamp is the most common. It's simple, low cost. You do trade up a little more board area because you got more components. Okay. And we will choose, when we design this circuit, we choose the clamp capacitance value to be large enough that the voltage is essentially constant. Okay. So what happens now when we turn off? We have the leakage, and now we have this clamp circuit, and then we have the clamp, okay, which is an RC, and we turn off. and we have the drain current going into the COSS like before. We have all this, we have the leakage current. But now, and then we have the path here of the reset, and we also have a path for the current to go into the clamp. So we're turning off, the MOSFET's now a switch. The drain current, the magnetizing current is driving into the drain, charging that capacitance, okay, just as before. And when that voltage on the drain is equal to the input plus the clamp, okay, what happens is now that current diverts into the clamp. No more current into the MOSFET. Okay, the drain current becomes 0. And now we go into the state where we have the current circulating just in this path here. So we're going to focus on this. We have this current circulating, the leakage, the magnetizing, just in the clamp circuit. There's no current here. There's no current on the input. This clamp interval has begun, and we're going to just focus on this part of the circuit. Okay? So let's just dive into this part. Just take the simple part where there's action going on in the circuit and look at this. The initial conditions are there's a voltage across the leakage, because we have this clamp voltage. We have this inductive divider between the leakage and the magnetizing inductance. And the leakage here is actually, it's going to be negative, right? Because this clamp voltage, the way we've defined the leakage, if we define the leakage voltage as positive in this direction, well, actually, because this is plus to minus because of the clamp, the leakage voltage is negative. And that's going to drive down the leakage current, the current in the leakage inductance over time. Okay? But we initially start out with just current flowing in this loop. There's nothing going to the secondary. That's the initial condition. Okay? So the leakage, the current here and here and here is all the same. But now, because that voltage is across here is negative, we're going to drive that current down. Okay? V equals L di dt. That voltage is negative. Di dt is going to be negative. But during this interval, okay, what's going on is that magnetizing current, so we said it's large. It's going to remain essentially constant. This clamp interval is measured in nanoseconds or tens of nanoseconds. So it remains, this current remains fairly, essentially constant. But because we have this negative voltage across this leakage inductance, we're going to drive that leakage current down to 0. And in fact, what I call this clamp interval will end when that current goes to 0. So what's during that time then, if we just look at this node here, okay, this current's constant, this current's decreasing, this current is increasing until it reaches the magnetizing current. And at that point then, the magnetizing current is circulating through that ideal transformer, and we're transferring the energy to the secondary. So we have this interval here, I call the clamp interval, where the leakage inductance current is ramping down. The current is the current is increasing in the secondary. Okay? And we're making that transfer to now we're delivering the power to the secondary. Okay? And so we can look at this, the power that's going into the clamp, okay, the voltage times the clamp current. Well, the clamp current is just equal to the leakage current. It's actually a negative power out of this. It's positive power into the clamp. And we will see that the power that's going into the clamp is power out of the leakage. The leakage current is delivering, the leakage inductance is delivering power to the clamp, but so is the magnetizing inductance. this is important, that during this interval, as we are transferring from this on time to the demagnetization or the reset time, the energy that's going into the clamp is not just the energy that was stored in the leakage inductance. We are taking energy also from the magnetizing inductance and delivering it to the clamp. And so this leakage inductance, it's not just the leakage inductance. The energy lost here is much greater than just the energy that was stored in the leakage. Okay? This isn't initially obvious, and this has been known for a long time, but it's just, why are we here? Because I don't see this being taught very often. And so the loss is much greater than just the half Li squared of the leakage inductance. So let's look at this a little bit graphically. What's going on in this clamp interval? I mean, the drain voltage is 0 during the on time, and then we turn off, and we've got this clamp interval. The magnetizing current is almost stable. The current in the leakage inductance is ramping down. The current in the secondary is ramping up. Okay. So let's see this. I'm going to run a simulation. This is a tool called Simplus. Okay, kind of a complicated. This has got the clamp. I'm going to model the clamp voltage as a constant. Here's our ideal transformer. We've got the leakage inductance, the switch. Okay. And you'll see here that we can see that this secondary current doesn't jump up instantly. It ramps down, and the current in the primary ramps down. Okay. So we're taking energy that should have gone to the output from the magnetizing inductance and turning it into the clamp. Let me zoom in on that a bit here. And you'll see this secondary current is ramping up while the current in the primary, while the leakage is ramping down. Okay, and this is like, 200 nanoseconds per division. This is taking a little bit of time. Okay, the voltage here is on the drain is clamped at the input plus the clamp voltage. Okay? So this really is happening in this interval here. Okay? So the clamp current starts at equal to the peak, and it ramps down. This is the leakage current also. The leakage current's ramping down. The drain current, or actually this is the diode current. The secondary current is ramping up. And so this is all lost energy and efficiency. I mean, ideally in the secondary, the secondary current would look like this. It would look like instantly jump up and then start ramping down during the demagnetization time. But it takes some time to ramp up. Okay. All of this area here, this is energy that was stored in the magnetizing inductance that should have gone to the output, but goes to the clamp instead. That's all lost energy. That hurts our efficiency. Okay. So kind of graphically, you can see this area here, that's lost energy. That hurts our efficiency. Okay. So it's not just the half Li squared of the leakage that's lost. We're diverting energy that we stored in the magnetizing inductance back to the clamp. So how much is that? Well, I put all the math in the presentation, and I'm not going to go through that. I do that because I really dislike it when professors put up an equation and then jump and just show you the result. So you can go back and on the replay or on the slides if you want to see how I derive this. But what we get is this result here, that the power in the clamp, okay, yes, it's proportional to the leakage, the energy that was stored in the leakage, the half Li squared of the leakage, but we have now this loss multiplier term. And it's related to the voltage we choose on the clamp and the reflected voltage from the output. So we choose this. This is part of our design We choose all this clamp and the reset. I mean, this reset voltage is the voltage, this difference is the voltage across the leakage inductance. This is the voltage reflected from the secondary. This is the voltage we chose for the clamp. The difference is what's applied to the leakage inductance. Okay? So the bigger this number, the bigger that voltage, the faster the current will ramp down in the leakage inductance. The faster the current ramps down in the leakage inductance, the less time we spend taking energy from the magnetizing inductance that should have gone to the output and diverting it to the clamp. So the bigger this difference, the less the power loss in the clamp. I mean, we always have this, but it gets multiplied. And we can plot that. I mean, it's a 1 over kind of thing. Okay? And so if we try and choose like a clamp voltage that's small, because we want a low voltage rating for our MOSFET, we end up multiplying that loss, that energy stored in the leakage inductance. The total clamp loss becomes many times that. And so the lesson here is that if you try and choose a low clamp voltage in order to have a low MOSFET voltage, because you're trying to have a low on resistance and minimize the conduction loss, you end up with this huge penalty in leakage loss due to the leakage. The clamp losses go way up. I mean, you'll have much more loss in the clamp than you ever saved in your MOSFET conduction losses. Okay? So I typically start with a design maybe that the clamp voltage is twice that reflected voltage. Okay? And that's some of the ways we can minimize the clamp loss through our design choices of turns ratio and clamp voltage. Okay? So just trying to minimize the clamp voltage to minimize the MOSFET voltage, you end up paying a real penalty in the clamp loss. But no matter what, we still want to minimize that leakage inductance because that minimizes the leakage, that initial loss, right? Even though we reduce the multiplier, we still want to reduce that energy stored in the leakage inductance. And so here's an example. This is pretty similar to what the Project Lab class I've taught at the University of Colorado, which is like a little LED driver, 25 at 25 watts of output, wide range of input, 100 volts to 375, 100 kilohertz. Okay. The output's about 20 volts at 1.2 amps, driving an LED module. So we end up with about 450 microhenries and a 7-to-1 turns ratio. We've got an auxiliary winding to power the primary control circuitry. We do have reinforced insulation. Okay. And so when we think about this, about the leakage, I mean, how do we minimize the leakage? It comes down to actually how we arrange the windings. With 3 windings, there's 6 basic different ways, 6 ways you can wind it. Primary, secondary, aux. You could put the aux closest to the core, then the secondary, the primary on the outside. Okay, maybe we're trying to capture all that leakage. Well, it turns out this is kind of your best starting point. With the primary closest to the core, then the secondary, and then the auxiliary winding. Okay. Now we can do even better if we split the primary. Now this complicates the winding and increases the cost, but this will greatly reduce the leakage inductance. Okay. This will give us a better coupling of the primary to the secondary. So let's see how this works. I'm going to jump now. I'm going to get out of PowerPoint. And I'm going to go over to the Frenetic platform. So here I'm logged into Frenetic, and I've chosen Flyback. I've put in all of the parameters, the turns ratio, the output power, okay. Here's my auxiliary winding. Okay. And I'm going to update. I'm going to let Frenetic do some quick calculation, and you'll see here I've got, let me turn on the magnifier. Oops. One of those talk to me. Okay, so I'm turning on my magnifier, and you can see it gives me the primary voltage and current, gives me the winding characteristics here. Okay. And I can also see that for the secondary. Here's the current winding down. Okay. Okay. And so it's done an initial calculation, and now we want to, like, let's design the flyback inductor. And so I choose suggested design, and I'm going to let it give me up to 3 designs. So it's thinking for a while. It's got a lot of work to do here. So you'll see some of the other things. There are some of the things in the Frenetic platform. There are some tools to optimize your core and look at the core and the core losses and the winding, the mechanical, the core and the bobbin and such, and then kind of a summary result. So while it's thinking, I mean, Frenetic is doing its thing. Okay, and we've got 3 choices here with an RM7 core, an E20 core, an RM8 core, and different. It gives you the weight, and I'm going to choose the one with the lowest loss. Now this is the biggest core, okay, and it's showing me a suggested winding with that interleaved, okay, and what do we have? So let's go look at the winding, because we're interested in leakage inductance. I turn on the magnifier again, and you'll see here it's giving you the winding, the current densities, and we've got about 1.7 microhenries of leakage. With 450 microhenries of magnetizing, that's actually pretty good. And it tells you what the skin losses are, the proximity, and the winding. There's no real, because there's no current flowing same time as in the primary, so there's really no proximity loss. Total 120 milliwatts of loss. DC resistance. Okay. Okay. And I'm in the US, so I've chosen American wire gauge. You can turn that into millimeter wire if you want to use the international, but I'm going to stick with the American because that's who I am. I'm using round wire. It's giving me and three parallels of 30 gauge. Okay. The primary, 2 strands of 32 gauge, and it's interleaved. But look, interleaving is troublesome. It adds cost. I mean, how bad would it be if I didn't interleave? So Frenetic, let's ask. So I turn off the interleaving. I'm still on the same core, and you'll see here. So all the primary is in one winding, and here's the secondary in one winding, and here's the auxiliary. And let's take a look. Oh, now I've got 5 microhenries of leakage versus like a little under 2. So I've more than doubled, and I've greatly increased the power dissipation. Okay. All right. So we don't want to do that. Okay. I mean, we do a lot better. You can see that we do a lot better if we interleave the windings. So let's go back to that. Okay. So good. You know, again, we are 1.7 something microhenries. That's a pretty big reduction. Okay. Now we can perhaps do a little better here on the secondary. Well, what if we We've got three in parallel with 30. So we're doing pretty good here. I'm going to change this. Maybe let's maybe make this a little bit easier. I'm going to like use fewer strands, a little easier to wind, and let's explore that. Okay, so the wire's a little thicker, a little easier to wind, but oops, our leakage has gone up. So, I mean, Frenetic actually kind of gave us, going back to, 3 strands of 30 gauge, actually gave us a very good solution right out of the gate. And so we can explore here, we could explore all different kinds of things. I mean, what if we did, Frenetic gives you this ability to explore all sorts, your different windings. I can customize if I want. I could say, what I could move the auxiliary. Let's get the auxiliary coupled closely to the secondary. Because we want good cross regulation. That auxiliary winding is powering our control circuitry. So we want that voltage to be fairly well controlled. Okay. And what happens now? Well, it's going to give me some complaints about high current density, so we'd have to address that issue, but we can explore that. But oops, our leakage inductance has gone up again, and then we expect that now because the primary is further apart. So okay, let's not do that. Let's put the auxiliary back on the outside. And we rerun the original solution. And we've got a pretty good result here at 1.7 microhenries out of 450. I mean, that's a fraction of a percent. That's a pretty good result. Okay. And total losses 420. So we're doing pretty well. So the Frenetic tool here gives us the ability, we can explore all of the different kinds of windings, configurations, wire. I mean, I'm using round wire. You could use lits. You could explore foil. A lot of different ways here, and you can do this very quickly here in a matter of seconds. You can explore various winding configurations, get the best combination of loss and leakage, and so pretty powerful tool here. All right, so we're coming up on an hour of time. I hope this has been useful to you. That the lesson, going back here, that this clamp multiplier, that the loss due to the leakage inductance in the flyback, it's not just this half Li squared of the leakage. You've got some design choices, this clamp voltage, the turns ratio, because that's set by this reflected, makes a big difference. Okay. And then the use of the Frenetic tool, you can just, it doesn't matter what this multiplier is, we want to minimize this leakage inductance, this energy stored. And so the Frenetic tool, gave us a way to do that. You saw we could get a very 4-to-1 reduction here over a very simple winding with the interleaving and then adjusting the various wire gauges and experiment. So Elizabeth, I'm going to turn it back to you if there's any questions that we want to answer. I hope people have found this interesting and useful. I know it was a little bit fast and furious, but you can watch the recording and we'll make the slides available, right?
Thank you, Bob, for the presentation today. I think everybody it's very satisfied with the lecture today with you. We have a couple of questions in the question and answer space. You have,
Okay,
I think
can we
you
see
can stop
that?
sharing. Yeah, if you stop sharing, you can see the questions in the yeah,
Okay.
in the both parts in the.
Okay. Does Frenetic Simulator do the interwinding capacity? I don't think that it does at this point. This question here. Another, why did I not interleave around the auxiliary? Okay, because the main power is, why do we not? Because the main power is in the output to the secondary. And so we want the best coupling between the primary and the secondary, because that's where the power is going. We want the power is going out the secondary. We want the best coupling between the primary and the secondary to actually kind of minimize that leakage. And I hope you saw there that, you know, when I tried that experiment of moving the auxiliary winding in coupling to the secondary, we actually increased the leakage inductance in the secondary and increased the loss. So that would give us a better cross regulation between the output and the auxiliary winding, but at the expense of greater leakage loss. And so again, this is an example. This is a great example of the frenetic tool. You can experiment right there on the tool. Move that winding around, you know, interleave however you want, rerun, get a better, you know, estimate of the leakage and the losses and the inductor, and then you know how the losses will go up with the leakage. So why? Because it gave us why did I interleave around the secondary? Because it gave us the best lowest leakage and it'll give us the least overall loss and power. Ways to discuss leakage inductance, both bottom wound and planar. The principles are the same, although with the planar, with the windings in a different direction. I'm kind of focused here on the bottom round, so we don't have enough time. PFC operation of the clamp flyback when it is operating. I don't understand this question, honestly. Power factor correction operation and clamp flyback when operating at DCM. I don't really see that. How do you select the core selection bobbin and wire gauge? Well, Frenetic did that for us. And it gave us, different choices. It gave us 3 different choices, the RM7, the E20, the RM8, showing us different choices of power loss versus like the size. I mean, the RM8 was a bigger core and heavier. It's gonna cost a little more, but it gave us the lowest loss because we ended up with the lower flux density. We didn't see that. But you could go through, you could explore choosing different cores and whatever. So with my experience in this, I said, hey, in this case, I'm going to go for better efficiency. I'm going to sacrifice. I'm going to take the bigger core, the RM8, and get a little better loss. That was my choice. But again, this is the power of the frenetic tool to allow you to explore. They've got pretty much every core in the world in there and every core material. So, and you can do it. You saw it took just seconds to make those explorations. That's faster than I could do it by hand or using MathCAD or Excel. So, lots of choices here. Is leakage affecting the output diode losses and temperature? Not so much the output diode losses. No, I mean the output diode losses are just the current, the peak, the average in the RMS current, and temperature. Well, yes, the leakage inductance, not a lot of affecting the loss within the inductor itself in DCM. Okay, that loss goes into the clamp. It affects the overall efficiency of the flyback. So less leakage, less loss, more efficient operation. So, okay, I think that's all the questions. Okay, oops, new posts. How do we
New
check proximity?
questions.
How do we, well, the skin effect, that's well known. Proximity, using Dowell's equations from the 1940s, his famous paper. Again, proximity loss is a function of the layers, and because it's the current distribution, fewer layers is less proximity loss. And so you can explore that if you want to explore like the different winding configurations. Again, Frenetic tool allows you to explore that. There's another solution in the clamp. What is another solution? Well, you minimize the leakage, and then there were choices I made around the turns ratio and the clamp voltage. I could go with a higher clamp voltage to minimize the clamp losses, but then I would have a higher voltage MOSFET. With the choices I had here with the clamp voltage and the 7-to-1 turns ratio, I ended up using a MOSFET around 900 or 950 volts rating. So those are still pretty readily available. The conduction loss still doesn't go too high, but I've minimized the clamp loss, the leakage loss. If I try to use a MOSFET around 650 volts, which are more common, like with server power, then I would have to reduce that clamp voltage, make that a lot lower, or change the turns ratio. So there's a lot of that's a whole nother webinar, optimizing that part of the design. So today we were focused on the leakage. How do we minimize the leakage? Understanding that the leakage is important, that the losses can be way greater, and then I showed you how to use the Frenetic tool to explore winding configurations to get to a minimum loss. Okay.
Yeah, I think we will need more hours to answer perfectly all the questions.
Yeah,
Very
we're up on an
interesting
hour now.
questions.
Yeah.
Yeah,
So
maybe we can
I do hope
explore.
people found this really useful and informative. So I think I saw that my friend and colleague Christophe Bassot was on. I had specifically invited him. Christophe is well known for his expertise in the flyback, although he's kind of moving on. He's doing like three-phase stuff. So Christophe, if you're here, great. I'm glad you were able to join us. Hopefully you can give me some feedback. Look forward to your expert guidance. All right. Well, thank you, Elizabeth. Thank you, Frenetic.
Yeah. Only to remember people after finishing this webinar, please take the advantage to use the link I have shared with you today, because this is not launched for now. So this is a special trial for all of you. Don't worry if you can open magnetic simulator part, because this is Frenetic AI is a special AI module. So if you don't have a pro license for magnetic simulator, it's obvious you can't go further to the magnetic simulator part. But if you need more information, assistance, you have more questions, you can contact directly with me or with any other member of our team. So thank you both for your time today. Maybe we can organize.
Do we have one moment to answer this question here? Do we have a moment, Elizabeth, or do we need to close the meeting?
No. I have time. Don't worry.
Okay. All right. Why are the primary windings and secondary out of phase with each other? Well, that's the way the flyback works. Because during the on time, the voltage in the primary is positive, and we're putting positive volt seconds onto the winding and storing flux and energy in the core. And then the secondary is negative. It's not conducting. That's just the way the flyback works. Is that they're out of phase. The flyback is an isolated buck boost. So we store energy during the on time. There's no during when the main switch is on, there's no energy being transferred directly through the inductor to the output. That's why it's an inductor and not a transformer. And then we turn the switch off, and the energy restored in the inductance and the flyback inductor is delivered to the output. It's like a buck boost, and that's why the windings are out of phase. So that would be like a whole nother discussion. So where should the primary split be located? The third, two secondaries with similar power. Okay, that's an interesting question. You can explore that in Frenetic, but you would put the two secondaries together and put the primary enclosing the two secondary windings. So that would be the way to arrange the windings if you have two secondaries with equal power, and that's not uncommon. I mean, you might have like a plus and minus output that all have similar power. So that's a good question. All right, I think we've. Oh, CU project file? Not really. I mean, the parameters are all there. I mean, I teach a whole course on, or I have taught in the past this whole course for a project lab for master's degree students, and they end up doing a flyback like this. So, does it generate a magnetic specification? Well, can we do that? Can I go back to that? If we got the time, let me share my screen because I think that's
we have time.
Okay,
People
yeah,
are
you're
still
back here.
here.
Yeah. So like here, I mean this data sheet aspect here of the Frenetic, here's the simulation results, the secondary, here's your mechanical, the core, the schematic, but also here's a bill of materials showing you all the materials, the wire, the core, the bobbin, the assembly, the winding, how to do the winding. So yeah, so all of this is here. Okay. Now, hey, one thing I didn't show you before is Frenetic can make you a sample, right? If you want to order a sample and the test data. So that question, does it give you a data sheet? Yeah, it's all right here. Frenetic gives you everything you need to build this and wind it. So yeah. Are there ways to recycle the leakage you would like to highlight? Well, again, that's a whole nother world. There is something called an active clamp flyback. Much more complex operation, but it does kind of recycle that and give you a better efficiency than just the passive clamp. But that's a whole nother discussion. But the active clamp flyback does recycle that lost power. Okay. All right.
Thank you, everybody. If you need something or you have problems to connect with or access Frenetic AI, please let me know. I have give you my email in the chat. So I'm writing for all of you. So if you have any problem, you can contact directly with me. So thank you, everybody, and see you at PCIM or in the next webinar. Bye-bye.